Okay, it's 9:30, so let's make a start for the first session of the day. My name's Kevin Maynell. I'm one of the members of the Apricot Program Committee, and this is the optics session. So this is actually one of my favorite topics, one of my first things that I worked in networking. And we have three really good speakers today. First of which is Mark Tinker, who probably needs little introduction. So he's been around the internet and the Apricot community for many years, and he's actually one of the Apricot program chairs. But in his day job, he's the co-founder and managing director of Transmission Co, which delivers wholesale DWDM transmission services in Africa. And he was previously the head of engineering at Seacom, which was Eastern and Southern Africa's first submarine cable system. So this talk is entitled Coherent Optics 101, which is about coherent pluggables in 100G plus G networks. Over to you, Mark.
Morning, everyone. So as Kevin spoke about, this will be a bit of another primer on coherent optics. And the reason that I think it's useful for the community is that as we get into more 100 gig, 400 gig, 800 gig capability on our routing and switching infrastructure, the likelihood that you're going to run into coherent plugs is quite high. And that's because coherent plugs make access to DWDM optics a lot more democratized, a lot easier than is the case today, where the majority of that access is restricted to your optical transmission teams. So just to talk a little bit about what coherent is. So many of you have heard about coherent optics, but for that, you need to go back a little bit and figure out what was happening before coherent. So before coherent, you essentially had what was known as amplitude modulation or intensity modulation with direct detection. And what that meant was that you encoded information on the amplitude of the light signal. Essentially, a voltage of 1 meant that it was bright, and a voltage of 0 meant it was dim. Simple as that. The modulation for that was what was known as on-off keying. So essentially, the laser goes on and goes off, switches on and off, and that's how you create a sine wave. The problem with on-off keying, or the problem with just amplitude modulation, was that it's problematic for high distances, and which leads to what is known as chromatic dispersion. So essentially, the spreading of light as it travels through the fiber. So that dispersion meant that you only had the ability to do 2.5 gig, and ultimately 10 gig was the most that you could do with IMDD modulation until coherent came along. So with coherent, we added other attributes to the system from the light to encode additional data. And that attribute was primarily phase. So with phase, which is another property of light, we're then able to encode additional information on each phase to create a lot more capacity in the system, just to make it really simple. The term coherent comes from the fact that you have phase coherence, in that even though the different optical signals are operating at different phases, the difference in the phase between them is actually the same. So that's the phase coherence. That's where the word coherent comes from. With that difference in phase and the additional data points on which you can encode information, now able to have, the 100 gig, the 400 gig, the 800 gig. And to add on top of that, we also add polarization. So if you have amplitude, you've got phase, and you've got polarization, you now have 3 attributes onto which you can encode data. And all of that is what makes it possible to move from 10 gig, 40 gig, all the way to 100 gig, up to 2.4 terabit, as we are seeing right now. So phase is another property of light that can be harnessed to encode additional information on the X and Y axis of the light signal. So those are the 3 areas that really make coherent work, and the reason why we're able to get so much capacity out of optical systems. The amplitude, which has been from day one, and now the phase, and then the polarization. So if you look at the history of where coherent came from, so as you can see, up until 2010-ish is where you had 10 gig, 40 gig, which was mostly based on IMDD before. So this is pre-coherent. And then you can see a sharp lift from about 2012 onwards, when coherent now becomes commercialized. Coherent research began in about 2008, and then in 2012 became commercialized. Especially in the subsea space. I think subsea space was the first application for coherent, because in that space, you couldn't get more than 10 gig on any subsea system. So you can see from that point, we're now getting to 100 gig, and then you get into large lambdas or wavelengths like 500 gig, 800 gig, 1.6, 2.4 tera. So at the heart of coherent is the DSP. The DSP, which is the digital signal processor, is where all the smarts occur. And the reason why the DSP is so important is that over the generations, the last 4 or 5 generations, since about 2010, the DSP has shrunk from easily 40 nanometer back in 2010 to 3 nanometer today. And in that space, you've gone from 40 gig coherent all the way to 1.6 terabit coherent. So the DSP does consume a significant amount of power, but that definitely does not outweigh the benefits you get in the increased capacity and increased intelligence. The DSP is also where we solve a lot of the linear and nonlinear impairments in fiber, specifically chromatic dispersion, is where you can solve it in the DSP. So you do not need dispersion compensation anymore in the fiber itself, which is how subsea systems used to get built, which is how fibers used to get built. If you look at Japan, for example, Japan is pretty much the only country that built dispersion shifted fiber, which was great back then, but you don't need that anymore. That means that you can run uncompensated fiber, which is much cheaper. In fact, with coherent, the more positively dispersed the cable is, the better the performance of coherent infrastructure. Some of the benefits that the DSP does provide, and what makes it possible to get to this kind of capability: soft decision FEC, which is basically forward error correction, but with more granularity. With FEC, essentially what you're trying to do is you're including parity data with the payload to make sure that you can correct for errors, which was hard decision FEC before. With soft decision FEC, what you're doing then is you're now adding more confidence on whether a 1 is a 1 or a 0 is a 0. And that soft decision FEC, even though it consumes additional bits in the payload, you go from about, let's say, 15% with hard FEC to about 37% with soft FEC. You essentially you improve what's known as the net coding gain, the NCG. You can improve as much as 12 to 15 dB with SD-FEC, which can translate to thousands more kilometers or significantly more bandwidth. And that's always the goal, to get as far and with as much capacity as you can. Spectral shaping. So spectral shaping essentially means that you can decide what shape the actual signal takes. You can have it either fall off less, you can have subcarriers in it, and in that, with subcarriers, you can have, let's say, multiple 25 gigs, multiple 50 gigs, multiple 100 gigs in one laser, which makes it a lot more efficient, and that's also done by the DSP. Probabilistic constellation shaping, PCS, is another new capability that's come online with the coherent technology. What PCS does is it concentrates the, what I'm looking for, within the optical constellation, where you have the symbols, it will concentrate the energy in the places that consume the least amount of power, which is normally inside within the constellation as opposed to the margins of the constellation. And that essentially makes it easier for the receiver to decode the information as it comes in. So with PCS, you're able to improve the detection of the transmitted signal on the other side. which makes it easier for you to increase distance and to increase capacity. We've already spoken about how chromatic and polarization dispersion is compensated for in the DSP, so both linear and nonlinear effects can be corrected in the DSP itself, meaning that you don't have to account for them in separate equipment. Modulation is much more increased. So as you saw before, but on-off keying, which is the concept of modulation in IMDD before, but in coherent, we rely on QAM and QPSK, which means that you're able to achieve, 1.6, 1.8, 2.4 terabit, and down the line 3.2 terabit. For example, now with let's say 64 QAM, you're able to have 800 gig on any subsea using 1.2 terabit line cards. And that's a real leap in capability. Layer 1 encryption is also now feasible with coherent. So, if you have customers like banks and things like that are looking for encryption at layer 1, the coherent DSP does that as well. The high transmit power is a really good one to have because then it means that you're able to transmit much further before you impact any loss, which then means that you can use fewer and fewer amplifiers within the line system, which reduces cost and also reduces the amount of noise that is generated from the amplifications. Some of the drawbacks of the DSP, obviously, they consume a lot more power. They are quite significantly expensive and very complex. And they do increase the amount of heat that's generated in the system. So one of the practical problems you have with coherent plugs is that you need to have a sufficiently cooled environment, especially in the chassis itself. If you look at systems that run 400 gig, for example, on QSFP-DD ports, you'll find that they don't have as many ports because just being able to maintain the thermal infrastructure on that platform is much more difficult. What's happening now, though, is that the SFP-DD, which is the same form factor as your standard SFP, SFP Plus, is now able to do 100 gig. So you can now fit 40 to 48 ports of 100 gig in a chassis. But with QSFP-DD, you probably have that down to half, if not a quarter. And just the sheer amount of heat that's generated is significant. But all that said, the benefits still outweigh those drawbacks because coherent is just leaps and bounds much more ahead than the previous technology. So if you look at a practical example of how coherent works, so you essentially take the modulation, and then you take the baud rate or the symbol rate. You multiply that also with the polarization, which we said is the X and Y axis. You take off about 20% to 35% of FEC overhead, and you achieve your bit rate that way. So any combination of modulation, symbol rate, and polarization, you can come out with a certain amount of capacity for a given amount of distance. Now, essentially, what happens is if you have a much higher distance, you want to go and have a much lower modulation because the possibility of what we call the optical eye being detected on the other side increases. The higher modulations get you more capacity, but then, as you can see, if you look at 64 QAM, you look at 32 QAM, 16 QAM, 8 QAM, and QPSK, you can see that the closer the symbols are together, the more difficult it is for the decoder to see it on the other side, which means the chances of errors are much higher. So with a higher modulation, you're going to compromise distance, but you're going to get a lot of capacity. Versus with a low modulation, you're going to compromise capacity, but you're going to get a much further distance. So if you're trying to look at, for example, a metro network of about, let's say, 30 kilometers or less, you can easily do 64 QAM and get 800 gig, let's say. But if you're looking at a subsea system doing maybe 12,000 kilometers, you're probably going to do QPSK or 8 QAM to get maybe 200-300 gig across that system. So it's always a balancing act. It's never always clear that the bandwidth capacity distance is a linear thing in subsea. It's always important to understand that you have to worry about distance, worry about amplification, worry about the modulation scheme to determine what kind of distance you can get for the capacity that you require. So that relationship is always, it's a moving target, let's say. It's nothing that's always fixed, but this is essentially how you can achieve the bit rates in coherent. So where do you find coherence? So traditionally, you'll find them in what we call embedded optics, so line cards in big chassis based systems. But now what's more interesting is that now you also get them in pluggables. So on the right-hand side, you'll see a pluggable, that's a 400 gig QSFP-DD. You now have coherent in QSFP28, 100 gig as well. That's now started shipping as of a month ago. And what that essentially means is that you don't need to spend a lot of money on optical equipment anymore. You can have a pluggable that's coherent with the DSP and all those technologies, the high power, the encryption, the PCS, the SDFEC, have that in your router, in your switch, which means that you can have 400 gig in your switch running, you know, anywhere from 100 to 800 kilometers, and you don't need to have an optical network. In fact, you can buy what is known as an alien wave service from an optical provider and say, I just want to buy an alien wave from your network, so you can give me the amplification so I don't have to build my own line system, and just plug that direct into your switch and router. So that can give you that point-to-point distance. And what this has really meant is that it's given, you know, ordinary folks like us in the IP space access to WDM infrastructure for, I don't know, a couple $1,000, let's say, versus almost $1 million to build a line system. And I think because of this, the chances that if you're going from 100 gig to 400 gig to 800 gig, you're going to run into a coherent plug. It's quite difficult to find gray plugs running at anything more than 100 gig nowadays. So for embedded, which is a traditional optical chassis that we've known for a long time, the use cases for these are typically ultra long haul. So you're talking subsea, you're talking 3,000 kilometers and above. The technology here is generally proprietary, but it is high capacity, it's high distance. That's the good thing. The bad news is that it tends to be quite expensive. You're talking millions of dollars for a large capacity system, for example. But then again, if you're building a, let's say, $500 million subsea system, it's not going to be a stretch. On the other hand, the pluggables will go into what I'm calling the new age optical systems, where the smarts are not in the line card, the smarts are in the plug, and the line card is just a transponder. That's all it is. There's a number of vendors out there who are building such systems, and this makes it quite easy and accessible to access those systems. These would be for metro to long haul applications. You're talking less than 2,000 kilometers. This would also be what is known these days as IP over DWDM. This is the actual IP over DWDM as opposed to what we had in 2008. And the plugs are now capable of 800 gig as of this year. And by the end of 25 or early 26, we should start seeing 1.6 terabits in a plug as well, OSFP XD, maybe QSFP. So that's actually quite interesting. And the thing now is that if you look at 400 gig QSFP-DD coherence, you're probably looking at about 300 kilometers max at maybe 200-300 gig. But with each generation, you're going to increase the distance. So with the 800 gig, you can probably do 600 kilometers at 400 gig. And with the 1.6 tera, you can probably get easily maybe 700 kilometers at 400 gig. So it's going to be interesting, I think, in the next 2 years, where the industry might come to an inflection point that operators who are spending money on traditional optical equipment might begin to struggle with other operators who are looking at systems such as these, because the cost flow for traditional infrastructure is reasonably high that the vendors can't go below that to offer a decent price. So I think there's going to be quite a bit of pressure from these kinds of systems on traditional infrastructure. So if you are trying to greenfield an optical network in the next 2 years, I'd probably look at this instead, because these will, I think these will work out to be cheaper per bit, and that gives you more competitive advantage in the market. The uncompensated fiber, I think, is a feature of coherent. And like I said before, before we had coherent, we had chromatic dispersion as being the biggest issue to performance in the optical space. And we countered that with having compensation in the fiber itself and also in the optical domain. With coherent, we actually like and prefer a fiber that is highly dispersed, because what then happens is dispersion creates a spread between the wavelengths. And as the wavelengths are more spread apart, the chances of them cross-talking together are reduced. That's a good thing. So by having a highly dispersed cable, you're going to solve for a nonlinear effect, such as crosstalk. What would then happen is once the signal arrives at the other end, the coherent detector will compensate for that linear dispersion and correct it before it becomes an issue. So cables now, especially subsea and also terrestrial, are what we call D+ or chromatic dispersion positive. Very, very highly dispersed. Would never work in the pre-coherent era, but in coherent, we'll have uncompensated fiber. It's much cheaper, it's much simpler to repair because you don't have to account for the compensation for dispersion. So yeah, so the main goal of any optical network is to carry as much capacity as far as possible. So that's what we call capacity reach. The DSP has obviously allowed us to do that. We still use standard EDFAs as they were invented back in the 80s. In the subsea space, the EDFA is a very low noise amplifier, which allows you to run high power without any impact. But obviously on the terrestrial side, the EDFAs are much simpler, and you want to have as few as possible to minimize noise. Coherent means that we can run an amplified system for as far as possible, as long as possible, before we have to consider regenerating. Because regeneration means that you have to drop from the optical space into the electrical space, and that increases your costs. So if we can amplify systems before we have to regen, that's the holy grail. And coherent allows us to do that. We're able to get really, really far distances. You're talking, ultra long haul, 6,000 to 12,000 kilometers, let's say, before you have to regen. And that plays a significant part in how successful the internet has been, to carry 99% of all that capacity on subsea and on terrestrial space. So for standardization is important now, and it's happening more often because coherent is being pushed by, so the OIF, which is the Optical Interoperability Forum, OpenROADM, OpenZR+, OpenXR are all bodies that are standardizing coherent, which means that it's possible for you to have one transceiver from a different vendor on the one end and another transceiver from another vendor on the other end, and it will just work for all the capabilities I showed you before. And that wasn't the case before. If you bought Infinera on one end, you had to buy Infinera on the other end. But now you can buy Ciena on one end and you can buy Infinera on the other end, and it will just work. Or an unknown vendor and a known vendor, it will just work. And this is the first time that we are seeing any kind of collaboration in the optical space. It has been a very closed market for a long time. And as much as the traditional vendors don't like this sort of thing, I think it's great for us. So that's good news, because then you can buy, let's say, a plug from a Flex Optics, for example, and a plug from a Smart Optics, for example, and they should both just work. And this is it's been made possible by these four standardization bodies. Yeah, so again, in terms of accessibility, coherent means that anybody can now build a WDM system for just about cheap, let's say. All you need is a coherent plug and your equipment, and you're good to go. You could extend that with a coherent plug in a line system, either owned by you or somebody else, and you're good to go. Or you could also build that further into a fully fledged optical system that's either from a traditional vendor, such as a Nokia, or a brand new vendor, such as a Packetlight, for example, or a Smart Optics. And yeah, with that, you can get anywhere from 100 to 800 gig in a plug, which is fantastic. So you're not paying for all the R&D that's going into building a specialized embedded optical line card. And that's really just means that anybody can have this technology now. It's not relegated to large operators anymore. And that's it. Thank you very much.
Okay, any questions for Mark? Okay, I'll ask one in that case. So the standardization, so how far has that progressed? I mean, is that available? You know, I mean, can you mix and match different vendor solutions today, or this is something that's coming at some point in the future?
Oh no, so you can do that today, especially in the pluggable space. So you can have different plugs from different vendors on either end, and that will work in coherent. What they're still working on is more on the orchestration side. So interfacing, provisioning between different vendors and stuff like that, that's not yet fully developed. But the most important thing right now where you can save a lot of money is the plugs. I think the orchestration isn't such a big deal because when you buy a traditional vendor, they're going to force their NMS upon you. So there's not much you can do about that. They'll probably fix that later. But the coherent plugs is a big one because easily, I'd say 50 to 60% of the cost of your line system is going to be in the transceivers. So that is a good breakaway.
All right, Jeff.
Jeff Houston. How stable is the signal-to-noise ratio on long-distance fiber optic systems, including both the transmitters and the cable itself?
By stable, what do you mean?
Encoding systems, particularly when you get into phase amplitude modulation, stretch your transmission across the power spectrum to the limit of what you can achieve in a signal-to-noise ratio environment. Better signal-to-noise ratio, you got more available points to actually use in encoding. The worse it gets, the fewer the points. If you set it up once and then use that forever, you're kind of encoding at the worst point, not the best point. And if the signal-to-noise ratio varies, you're unable to make use of it. And so the real question in my mind is, when we do this set and forget with various forms of encoding in our transceivers, are we suboptimally using the available capacity? Whereas we could, if it was dynamic, and dynamic enough that if you had more encoding points, you could use them, it would make actually a more efficient signaling. So the real question is, what is the nature of signal to noise? Now, we know it's temperature sensitive. I'm not sure what other variables go into fiber optic systems other than temperature. Do you know?
So it is dynamic. So it can be dynamic in how you optimize the system. What they're working on is to make it dynamic automatically, but that doesn't make any sense yet because WDM is, as you know.
I'm sorry,
Right.
5G, Starlink, even 4G, do it per frame.
Right. So what I mean for the optical space is, so you've got different modulation schemes that you can apply. And like I said, if you have a reasonably high OSNR, you can have a reasonably higher margin, so you can have a higher modulation scheme. But that will take into account a lot of things, like you said, the quality of the fiber, the distance, the capacity you want to carry, etc. So you can tune for the conditions. If you've got really bad fiber, let's say, not even high, let's say 20 kilometers, just really bad fiber, you're talking maybe 0.5, 0.6, 0.8 dB per kilometer loss, you can tune for QPSK at 200 gig waves, and that would be just perfect.
But what if it's bad for 1 minute every hour? And it's good for the rest. This is what I'm talking about. What if it gets dynamic? And my suspicion is, though I've never seen data, that particularly for land-based systems, the signal-to-noise ratio isn't steady. And we tend to tune for the worst case, not the best case, because if you tune for the best case, you just lose data. And the rest of the world has gone into dynamic optimization. But it seems the fiber world is still 5 years behind that, going, no, we're just banging the rocks together and having a really good time.
OSNR oscillation is not that aggressive in real life, actually. There's enough margin, which we call the DBQ or the DB quality margin, for you to pick a modulation scheme that's reasonably stable, even with a 5, 10, 15% movement in OSNR. It's not really that dynamic. I mean, if you take, for example, like the best modulation scheme, which is QPSK or 8 QAM, you can have easily 8, 9, dBq margin. And with that, any oscillation in the fiber, a truck moving over the road that causes vibration or something like this will not create any significant problems. The OSNR movement is not that significant, but the biggest gain is FEC. So FEC is how we gain the OSNR. We don't gain more power, but we just reduce the threshold at which the OSNR can get really bad.
But FEC isn't reactive either, is it?
No. So it's not reactive. No.
Yeah.
So you're planning for the worst. Yeah. It's not a moving target like that. But there's enough margin that even when you have a drop in OSNR, it's not going to impact the quality for the modulation scheme.
Okay. I think we need to move to the next talk. So I think suggest take it to the coffee break in an hour or so.
Sure.
So thank you very much, Mark. Thanks once again. Okay, so second talk. We have Reza Roku, who is a senior director, SDN application architect at Ciena. So he's currently working on multi-layer IP over DWDM networks. Keep tripping up over that. So he's been working in the industry for 2 decades and has also authored standards documents for the IETF and the Broadband Forum. So his talk is entitled Coherent Pluggables in Multi-Layer, Multi-Vendor Packet over Optical Networks, which is about, again, small form factor pluggables inside routers and their use cases. Over to you.
Okay, thank you very much. I'm continuing the discussion from the second last question that we had. Mark started about the pluggables, what the pluggables are. And the second last question was, what about putting that component in a network and look at the holistically from the network perspective, what will happen? And the network could be optical photonics, IP, or IP over DWDM. So how is going to work? So how these components, when we look at the component from the network perspective, how it's going to work? And the next question is, why this matters to you? Why you should even care? So we continue that journey that we have started from the component. Now we go towards the network view and how it's going to work. My name is Reza Roku. As mentioned, I am based in Canada, Ciena, Canada. And thanks, Mark mentioned Ciena a couple of times about the pluggables that we have. And we will see how everything works together. The perspective that I have here is from the standardization. Mark talked about the OIF, which is the standardization for plugs. We have IETF, a standardization for the network perspective. How is going to work? How these are related to each other? And how it's going to affect you day-to-day life? You know, why it should even matters to you? So these are the area that we are going to talk about. I started from bigger picture. I narrow it down to a small thing and say, what are the tangible stuff that we have to care, maybe now or very near future? So when we talk about pluggables, oh, we went very fast. The problem that we want to solve is here. The routers, that small thing that you see at the bottom left is a pluggable that Mark was talking about. I put that one inside a host. In most cases, at least for a discussion of this meeting, the host is a router. We are creating an IP network that overlay on top of the underlay, and there is that cloud controller, multi-layer controller, single controller, IP optical. I will cover what it means, but this is the general area that we want to cover. The persona that I'm looking at, I am an IP MPLS engineer, or I am a photonic engineer. Depends on what you have. The concept might be a bit different, but overall, the picture should be that I am looking at the network. Now I put the plug into the router. It used to be a separate component altogether. Now it's inside the router. So is this part of the routing domain? Is this part of optical domain? Either. So these are the questions that we want to do. And problem that we want to address is that pluggable is there. How I'm going to do the lifecycle management, meaning I put it there, I have to configure it, provision it, optimize it, collect telemetry data, PM, alarm, and so forth. So the whole idea how it's going to work. So these are the areas that we are going to talk. So I'm going to skip this phase because already Mark talks about that one. The problem statement is important. Just look at the right-hand side of this picture. I have router plus pluggable plus optical photonic. So how everything is going to work. So, and this is the dilemma that we want to do, and mentioned a few times about NMS. I put it in the context of the SDN controller, IP, optical, or multi-layer. So before doing that, I'm part of the IETF. The work that I'm showing here is part of the few draft that we have. I just want to acknowledge the work that we done is a group of vendor and operator get together and try to address whatever you see here. So let's start from the very high level. I have two routers connected through an IP link. From the perspective of the router, it doesn't really matter how this IP link is created, whether or not it goes directly or it goes through the photonic and optical. From the router perspective, I have IP link of 400 gig. As simple as that. It's very simple. But in reality, between two routers, is the typical example. I have component called transponder, the one that Mark just mentioned. Take the signal, coherent, goes to the middle part, ROADM, which is the photonic line system. Basically, it's doing the switching of the light, and other end is doing exactly the reverse side. So the important aspect of this discussion here is, when we talk about that IP link, I'm creating a layer 0 service, optical service, photonic service. And there is a mapping between IP and photonic. The important aspect is that arrow. There is one-to-one, one-to-many, or many-to-one relationship. In other words, when you see an IP link, think of there is somewhere an optical line, optical service that is servicing that IP. Consider photonic as an underlay. On top of that is an IP. An IP you can create even going up, create the optical IP tunnels and IP service on top as well. So with that, let's expand this one, how this is going to relate to the pluggables. Same picture, I just take physically the transponder, put it inside the router. This becomes pluggable. From the logical perspective, I'm oversimplifying it, but from our discussion, it doesn't matter. I have still an optical service from plug to plug, which IP link right on top of that. So, and this is a context that we have to consider. One is any IP link has an associated with the physical or photonic lines service, and the concept of the transponder is pushed inside the router. So another thing that is important also, very bottom of this one, you hear pluggables, coherent pluggable, optical pluggable, all of them are the same. So basically different terminology for the same thing. Continue with the same network that we have. It might, somebody thinks that, oh, we are going to remove every transponder in the world, put it inside the router. But this is not the case. I'm expanding to that network of router 1 and 2. Now I'm adding router 3 and 4. I'm creating another IP link. You will see IP link 1 is going through the pluggables, and for IP link 2 is going through the transponder. From the network perspective, the whole discussion today is a network perspective and how to manage it. From that aspect, I create a heterogeneous system which combines routers, optical, pluggables, expander, meaning transponder or muxpander, and ROADMs, line system. The whole idea here is, for foreseeable future, this is the ecosystem that we have to work on. And any system, any IP optical multi-layer control that we want to introduce to this network should appear to that. Basically, it should stick to this dilemma that I have a network, there is pluggables, maybe there are pluggables, maybe there are transponders, and maybe there are both of them together, and how we can manage it. Because sometimes when you look at the slide 2 that I showed, people think that, oh, I have router plugs, and that's it. This is the network that I have to design for the control, which is not the case. I want to bring that awareness here. So another aspect that we have to consider going through whole process is the concept of the multi-layer. I have a network at the bottom of this page. mix of router, plug, transponder, and from the photonic layer 0 all the way to layer 2.5 and 3 IP and PLS network, there is a correlation. That correlation is from the configuration perspective, from the collection of the telemetry, PM alarms, from the optimization, from everything. Whatever design we want to have for the control of that system should adhere or should consider this one. All aspects of life cycle management of pluggable in the context of a network. So this is a short summary. I'm not going to talk about that one. The last item is important. Ciena, as you know, we introduced multi-layer concept, not from the perspective of defining it, but how to implement it in the network. There are few categories we define. Very last one is lifecycle management of the coherent pluggable, which is relevant to our discussion today. So now I'm narrowing down. I started from the big network. I'm going to the pluggable from, again, network and modeling, considering the fact that I know what's going on in the pluggable. Mark talked about that one, the physical aspect of the DSP modulation and everything else. So from the pluggable perspective, there is two sides, logical two sides. One side, which is photonic and optical side. Basically, it goes to the optical line system. That side, if you heard about some term, I put some terminology here, just trigger if you heard about, for example, operational mode or mode ID, media ID. These are basically referencing this side. And that one is based, in most cases, host router should not care about that. If the modulation is a QAM or is a PSK, what difference does it make to the router? Router wants a port of 400 gig. From that aspect, the characteristic of the optical side is, in most cases, I cannot say 100%, in most cases, a very big percentage is not relevant to that. And this media ID that you see here, this number, just hold on to it for a moment, is referring to a bunch of attributes on that side. We will talk about that, just a trigger point for the next slide that I have. On the other side, host ID, which is the electrical connection of the plug to the router, definitely router or host should be aware of what is happening there. So again, host ID is something that if you are familiar with OIF, for example, you heard this terminology over and over again. And I put it there that in most cases, host shall be aware of all the attribute and characteristic of that. So having these two sides of that, let's go through a simple example. This is not trying to give a whole context of this media ID and host ID, but just giving an example. These are something that at least trigger our discussion in a tangible way. If you heard about for example, these two numbers, 11 and 3E. If you are familiar with OIF, I'm sure you heard about this one. This is ZR and ZR plus, for example. The whole idea here is just forget about everything in this table. Number 3E, which is a media ID, is pointing to a specific modulation, a specific bit rate, a specific lane count. So instead of putting all this information, I said media ID is 3E, and that one is basically pointing me to a bunch of attributes. Same thing from the host ID. Host ID 11 is pointing to a bunch of attributes on the electrical side. So just imagine that when I'm talking about the characteristic of pluggable, two numbers is referring to the characteristic that I want to implement in the pluggable. So starting from the router relationship to the pluggables. Mark talks about OIF. OIF developed this quote-unquote protocol, CMIS protocol, which basically internal to the router. When you put a pluggable inside the router, they talk to each other through that channel. It's the memory-based that they work. But at the end of the day, this is something which is not visible from outside the router. I cannot go and say, okay, change CMIS of something to something else from the northbound of the router. That is just internal communication channel between the router and pluggables. Continue with that one. I'm going to skip this one, but if somebody is interested to know what, I'm going to skip it because it doesn't change our discussion. Now, keep going with the router to plugs. I started with a one router, one plugs. Now I'm creating a network. I'm putting a layer on top of that for the controller. How many of them we will talk about, but this one is trying to say that how a controller layer can get information from the pluggables. The whole idea here is information from pluggables is coming from northbound of the interface of the router. Basically, I cannot go and tell it to the pluggable and say, okay, give me whatever you have, I want to configure you something. I have to go through the interface of the router to do whatever I want to do for the configuration, for the discovery and collection of the telemetry and alarm. This is an important aspect because it shows that now there is a relationship between modeling of the router and pluggables. It's not as simple as just do whatever you want to do for pluggables and everything works. And you will see at the beginning, the problem might be very straightforward. I put the plugin inside router, everything works. But you will see we are getting to the detailed discussion that there are lots of things should happen if we want to go with that logic of the plug and play. So we started from very high, we go to the router, we talk about pluggables, now going through the chain of the control. Now we are getting to the control area of the pluggables. If I blow up the router and pluggables, this is the picture I see. Again, these are the logical component that you see inside the host vendor Y. For example, there is a router from vendor Y. I put pluggable from vendor Y and X. That third party, the multi-vendor aspect come to the picture here that I put two pluggables from two different vendors inside the router. So media side, host side, we talked about that one. Continue with that. The relationship inside the router is defined by the CMIS, OIF. OIF is the organization which is defining CMIS. We talked about that, a few minutes ago. From the northbound of the router, we are exposing the characteristic of the router and pluggable to the outside world. And this is the work of IETF. How the characteristics of pluggable should be exposed, which data model to use, how to do it, how they are related. If I don't even say anything, you should assume that these two protocols should work together if I want to really have a workable system. CMIS should work between plug and router to convey information, and the router and outside should work with the IETF. So in other words, if I want to make sure everything works when I put the plug and everything works, these two protocols, these two organizations should work together. And this is the whole idea of bringing the ecosystem of the various standardization organizations together to say, yes, it is important to have a working relationship. And this is one of the things that CNI is doing. We are very strong at OIF, we are strong at IETF, again, with the collaboration group of vendors and operators. Suffice to say that this is a group activity for the industry. We are part of that ecosystem. So continuing with the same theme, it is important now we reach to that conclusion that it is important to do some level of the modeling of the pluggables. And these are the components. If you blow up the pluggables, these are the components of the pluggable that we try to address it as we go through the modeling. The detail of that might not be important for us. The important aspect here is that when we want to model that pluggable, we have to make sure we are adhering to the photonic optical side and the electrical host side. So these are the important aspects. The detail of that might not be relevant. So the work that we do at IETF, again, look at the IETF as a holistic network or service perspective. I'm creating a network and I want to create a group of IP links. As a result, I have to create a group of optical services. We just said that there is a correlation between them. If we want to do that, the goal of IETF to model pluggables from the northbound router is to have that ecosystem, multi-vendor, multi-layer plug and play. You put the plug, the router is able to communicate with the plug, even if the plug has some attribute that the router doesn't understand. It should stick to the common denominator. Plug comes up, discover that, and from the northbound, I should be able to configure that pluggable, at least some of the standards, and if there is a proprietary or the vendor agnostic characteristic, how we want to address it. These are the things that we want to address going forward. There are two activities happening at IETF. Again, I'm oversimplifying it, but just giving you a context. One is operator driven. For the operators like Gloserve, you might not even care how I'm going to control that pluggable. You say, my use cases are discovery, service provisioning, alarm correlation, layer 0 to layer 3, the multi-layer, the coordination, and so forth. So they define those use cases. And the activity is a vendor-driven. That I'm part of both, but we divide it that way logically because we want to make sure that there are use cases and also underlay the modeling which address that use cases. And we thought this is a very good way of putting it because traditionally, sometimes we go and design the model for the controlling, for example, something in this case pluggable, and we go and say, let's find the use cases which can be addressed by this. Now, we're going the other way around. We say, this is a use case. I have to design the modeling which address that use cases. So in both cases, vendor and operator really work together. If you go to either of these drafts that I will show you, you will see when I said, for example, operator driven doesn't mean that vendors are not there and vice versa. So, but this is a main theme that we have. There are two activities that I mentioned, operator driven, vendor driven. So this is a vendor driven. The goal here is if I want to model the pluggables, IETF has a bunch of attributes and Yang model to define various aspects of pluggable, but there are other standardization, forum as well, TAPI, OIF, ITUT. We want to make sure that we are not reinventing the wheel and we are really open-minded about using anybody that has anything. You know, OpenConfig might have very good attributes and a TAPI and others. So we went through all these. Now this is work in progress. We go through all the attributes which are defining the characteristic of the pluggables. And we say it doesn't matter which the forum or standard body is defining. We go and try to be putting all this together and do the gap analysis. We said these are the things that is missing from IETF, and eventually we define that missing attributes that should be included in the work that we do at IETF. But this is an important aspect. We know that this is time sensitive as well. We know that we have to finish this as soon as we can, but there is a very good progress between the vendors and operators to go through that. Again, I put the reference to the draft there if you are interested, or if you are interested to be part of that. I'm encouraging you to come and let's talk. And by all means, I really want to have the contribution of all of you to this work, because whatever we do, there might be something missing. And if you are interested, please reach out after the meeting. And this is the operator-driven draft that basically defining the use cases that operator wants. The use cases are discovery of pluggable. If I cannot discover it, the rest is irrelevant. You know, how I am going to discover it, how to inventorize the pluggables, discovery of layer 0. Everything is discovery and read only. Whatever I have in the network, I'm going to read it. And the second part is, now I'm going to create provision services, layer 0 services, layer 2 and 3 services, doing the correlation between underlay and overlay and so forth. Again, this is there is a reference here to the draft. And the important aspect here is if you heard about TIP, the Telecom Infra Project, this draft is basically adhering and is aligned fully with that. Now we're going up to the chain. We have started from the router plugs, and now we're going to a controller. I'm sure lots of you think, okay, how I'm going to control it as an IP engineer, persona IP engineer, or photonic optical engineer, how I'm going to do it, what is happening inside that router might not be that important and relevant. The important aspect is how I'm going to do it. I put a cloud here and I intentionally call it IP control. I didn't call it IP controller. Optical control and multi-layer control. Why? Because these components are logical component that says that I need to have IP functionality to control the IP network. It doesn't say that there is a single box to do it. If you go with that mentality, means how to realize it. Now that IP logical component, how is going to be realized? Is it one box, two boxes from one vendor, from two vendors? This is very important that we have to consider and differentiate between the logical component for the optical control, for example. We need to have a logical component inside the network to look at the service end-to-end, pluggable to pluggable, for example, for the provisioning, collection of a telemetry, optimization, everything. Whether or not that single box is in realization part, the two box from two different vendors or is from one, it's relevant. It doesn't really matter for discussion here. And the important aspect, at least for the optical side here, is that optical control block should basically do all these things: planning, viability, provisioning, collection of the telemetry, and so forth. And it's just very important aspect to consider as a part of that logical entity. Just for an example, I put two realization of that. This is just two of them as an example. It could be any combination you want. Now, I call it controller. You see outside, everything is controller. Now, these are realization. I can go from three vendors, from IP controller, optical controller, multi-layer controller. Or I can take the same concept that I have. I have one controller from one vendor, which is doing the IP, optical, and multi-layer control. So make a difference, the distinction between logical IP control and realization. Because in most cases, if I show you this picture and I don't say anything, I'm sure 99% of you think that there are three boxes that I'm saying that I have to have this architecture to create the network. But this is not the intention. Intention is to just give you the logical perspective of that. So there are lots of detail that if you are interested, we can have a discussion after the meeting. But I just want to finish up the discussion today with another work that is happening at the IETF. That work is on hold for now, but I'm going to acknowledge that one because this is something that the IETF was working. We are waiting for the result of the first two work that I just described. But if somebody asks me, what are the potential way of realizing the controller layer? Again, these are, I put it, work in progress. There are various options that you can have. For example, one option could be now you see everywhere you see controller, meaning these are realization. This is, we are saying, is a one box which is doing IP. Everything that you see here, and the acronym that put here, it's coming from IT. It doesn't matter for our discussion. The first thing from the pluggable perspective, as you see here, if I go one more, you see the animation here. From the northbound of the router, we are collecting the read-only plug state and telemetry data, goes to the optical control, because at the end of the day, optical control should have the end-to-end visibility, as we discussed previously. There is an option two. There is no relationship between any of these. The simplest one, there is a router, northbound of the router, anything that we want to do for pluggable goes through that. There might be another one that basically there is a read-only, read-write from the pluggable to optical. So each one has a pros and cons. Which one is good or bad? There is no good and bad. All of them are valid. The whole idea of this work that I'm showing, and it's still in progress, as I clearly mentioned, in the future might be option 4, 5, 6, 7. You can come up with any way that you want to control this network. And all of them are valid. depends on what you want to do, depends on your ecosystem of the control that you have today. Maybe one of those options is better for you. It doesn't mean that necessarily this is a good or bad. It's suitable for you as an operator. And this is important to consider. And the work that we do at IETF, we try to basically promote that idea that these are the tools in your toolbox. If you want to use it, go ahead and use it. Maybe it's good for one operator, is not good for the other for the various reasons. So if I summarize it, for the IP network, IP MPLS, the persona of the network operator at IP MPLS network, coherent pluggables are appearing, it's coming. Maybe it's not, you don't have it in your network. Maybe you are thinking about that within your network. The idea here is coming. Maybe it's this year or next year. And like it or not, we have to think about it, how to do it. We used to have two separate departments for optical IP, but it's not the case anymore. As you see here, the industry is changing from that aspect. Maybe some internal behavior of the operator should, align with that logic that I put the pluggable inside the router, and the whole idea is going beyond that. You will see plugs coming. Mark mentions various reasons of that, from the economy perspective of that, and depends on the network that you have. Are we talking about the access metro, aggregation, or core? So all this, but the important aspect that whatever we have here is you have to have experience with IP over DWDM, including coherent pluggables. So that is the whole idea of the message that I mentioned here. And I can go maybe 1 minute. Standards are merging together to address this issue. Operators have a strong will to do it. Same thing as a collaboration with other vendors. And the important aspect here is lifecycle management pluggables. And with that one, I see the red light is flashing here, which means that the time is out.
Yeah,
And
perfect.
maybe we have
Thank you.
time for one question.
Yes, of course. If there's any questions, going. On.
If there is anything, reach out. If you have some discussion that we want to have for some of this that I skip, we can have a further discussion and deep dive. Okay.
Right.
Thank you
very much. Thanks. Okay, so we now have our final speaker. This is Rishab Tata. So he is a technical marketing engineer at Cisco, working in layer 3 routing platforms. Previously worked for the Nehru National Institute of Technology in India, and also IBM as a security delivery specialist and sysadmin. So his talk is entitled Passive Optical Networks and the Future of Fiber Connectivity. So this is really about their evolution and how they can play a role in the next generation of broadband networks. So over to you.
Hello. Yeah. Thank you and good morning, everyone. And thanks for joining this session. This is going to be a really interesting session on the passive optical networks and the future of fiber connectivity. I am Rishab Tarte, a technical marketing engineer working with Cisco currently. And without further delay, let's get right into the agenda for today. So what we are going to look upon and what details are we going to talk about today in this session. So we all know, like, we have to understand, first of all, the details or the basics of these networks, like what exactly are the passive optical networks. We will talk about what is going to be the history, what was the history of these passive optical networks that we know of, and how did it evolve over the period of time. And then we will talk about the various components that make up this PON network as we know of. We will talk about the internals, what are the optical splitters, split ratios, and insertion losses. We will talk about the working principles of how it works in the upstream and the downstream direction. We will also take a look at what are the new advancements that are happening, which is also known as RPON or the routed PON technology. And then with this, we will move towards the role and the advancement that are happening on top of it using the BNG that we know of. And in the end, towards the end, we will look at the new use cases and the final key takeaways. So first of all, what is a passive optical network? Now, the passive optical network as the definition says, it's a high-speed, cost-effective fiber optic communication system. Essentially, it uses a point-to-multipoint architecture to deliver data from the operator side all the way to the user end. Now, over here, this data could either be internet traffic, it could be video services, it could be business applications, it could be voice traffic. I mean, it could be either of them. When we talk about internet traffic, it could be web browsing that we do, the video streamings that happened over the period of time. We'll talk about, and then in the video services, we have IPTVs and other use cases that we know of. Now, how it evolved over this period of time. So initially, we had the copper-based network lines back in 1980s, which were like the initial systems, right? And then we moved towards the DSL and cable modems, which got us to a little higher speeds of data in terms of transmission. Now, and then we moved to the point-to-point fiber, okay, which allowed us to have gigabit levels, right? So initially we were at a very lower speed, then moderate speed, and then we got to some gigabit level of speed, and then additional parameters we got, such as the latency, advanced lower latencies and able to transmit over the longer distances. These abilities also we achieved through using it. And then finally we introduced the PON, which was again a cost-effective fiber technology for long distances. We can have symmetry in these. We will talk about all these terms, what are symmetrical data rates. Okay, so initially when we had the early PON era, we were having the basic PON, like the A PON, B PON, G PON, with their speeds as we see here, right? Like the 54 all the way up to still very less up until 125 GB. Then we moved to the PON era, where we had GPON, XGPON, and XGPON. I would like to focus everyone here on the XGS PON here. This is something new that is coming here. We will talk about in the coming slides. And then we have the next gen PON era that is also coming up with the NG-PON and the 50GS PON. So before we move ahead, a quick recap on the PON networks that we know. We have essentially three major components in a PON network. The first one is an OLT, the second is a passive optical splitter, and the third one is an ONT. Okay. Now we will look at where these specific components sit in these PON network as we know of. So in a conventional PON architecture, moving from the left all the way towards the right, we have a core network, which will be having service provider infrastructure, which will be connecting us to different power points, internet, voice over IP, enterprise network, DCI, peering, everything. And towards the edge of this core network, we will somewhere have an access router, okay? Now to this access router, we'll be connecting the OLT that we saw, and then a passive optical splitter, and then the ONTs. Okay, and all these and the passive optical splitter here forms up the optical distribution network that we know of. So OLT terminates all the users' networks onto the single central office. Then we will have the ONTs that we talked about that will be sitting on the user side. Then we will be having the optical distribution network, which again, as we spoke about, will be the passive optical splitter. And essentially, all this combined together will form the conventional architecture. And this is how these devices sit over here as we saw. So now let's look at the details of these particular or definitions of the conventional PON architecture and what are these specific definitions that we need to understand first of all. The first thing is the optical splitter. What exactly is an optical splitter? Then we will talk about the split ratios and then the insertion loss. The optical splitter is nothing but a device that basically splits your light into specific ratios. The ratio could be 1:2, 1:4, 1:8, depending upon the split ratio of that particular splitter, right? And every time you split the light, there is going to be some loss into it. And the loss is something known as the insertion loss. The insertion loss here is calculated by 10 log n, where n is the number of splits that you're performing on top of your optical splitter. And plus there is a sigma E factor also. So sigma E here is the additional losses that occur, which is maybe because of the manufacturing imperfections, or it could be because of the waveguide misalignments. The important thing to understand here is that once you're designing a PON network, you have to make sure that your end-to-end link budget is within the threshold or within the limit which I've calculated, to make sure that there is no power loss and you can have an effective transmission and reception over that particular PON link. On the right hand side, I have given some typical split ratios with sigma E as 0. Now, let's look at how does these pawn network works and what are the working principles of the pawn network. Okay, so we essentially have two streams that will be working here, the upstream and the downstream. They will be having different wavelengths. Okay, and the WDM specifically uses, pawn uses WDM as this infrastructure to transmit light both in the upstream and the downstream direction. So, but in this case, in the downstream direction, it is always a broadcast, and in the upstream direction, it's going to be a TDMA mode or the time slots based mode, right? Let's look into it now, how basically the WDM first of all works, and then we will move into the upstream and the downstream data transmission over these networks. So we know we need to have specific upstream and downstream wavelengths to make sure that there are no interference in the network or in your PON network. To make sure that happens, we need to specify distinct wavelength for the upstream direction and then the downstream direction. As we see here, for an example, the range of 1260 nanometer to 1360 nanometer for upstream traffic can be used, and similarly for the downstream traffic, other range from 1480 to 1580. Now, because of when we are using the specific wavelength, we have to make sure that we avoid interference as well, and we give some channel spacing in between different channel spacing in different wavelength to make sure that there is no interference and your signal can pass through easily. Okay, so coming back to the PON, in the downstream direction, how it happens, let's look at it. So as we talked about, in the downstream direction, it's going to be a broadcast. Okay, so we have the OLT and the ONTs. The OLTs is broadcasting the downstream traffic to all the ONTs out there, okay? Depending upon the split ratio that is there. Now, how each specific ONT will take the specific information which it needs based on the port ID or XGM ID that we know of. So there is a XGM ID or a port ID or a ONT ID. So the specific to that particular user or specific to that ONT, the specific data is transmitted or taken out from that broadcast wavelength. Okay, and the next thing that we need to take care of or take an understanding of is that the downstream transmission operates in a continuous mode. That is, the laser is always on in this case, even if there is, and it can only be turned off only when you exclusively turn it off. So we have to make sure that it's on all the time. And again, in the upstream direction, it gets a little interesting. In the upstream direction, we use TDMA or time division multiple access to make sure that an exclusive time slot is provided to each of the ONT to transmit to upwards toward the OLT. Now, during the sending of this data, the PON network has to make sure that the specific ONT is transmitting to in its given time slot only. So if ONT 1 is having a specific time slot, it will be standing into that time slot only, following the same, and they cannot interfere. And there has to be something known as a guard band that has to be there to make sure that that the time slots do not overlap. The next thing that you have to make sure is to optimize the transmission timing. You have to make sure that your distance from the OLT to the ONT is calculated, and based on that, the specific time slot is allotted, so that you don't end up sending signals from ONT2 in the time slot which was provided to the ONT1. So for that, there's a process known as ranging that you have to perform before essentially forming these links and giving these specific time slots to the endpoints. Okay, and one last thing to notice is that even if some particular ONT is not sending any data, we have to make sure that that particular slot is kept empty, so there is less congestion on the overall link. Now, in the initial slide, we talked about the XGS PON, and we said, so let's look at the ITU-T standards that are there. Okay. Now, we had initially GPON. We have also talked about the downstream rate, the upstream wavelength, downstream wavelength. If you see here, we have XGPON and XGS PON, right? So what is a specific unique difference here? So in the XGS PON, if you see, the upstream and the downstream rates are symmetrical, which is something new that is happening when compared to the XGPON, which is having downstream as 10 and upstream as 2.5. Because of this symmetricity, we can now have a symmetrical rate on both the direction, that is on the up and the down side. We have also talked about the split ratios and what are they followed for the specific standard. Now, what is new happening? We have understood that what is the traditional architecture and how it works. We have a access router at the end, then we have a OLT, and then ONT is going towards the end. But what is new that is happening into the PON architecture? So essentially, with the new routed PON architecture, the entire OLT is now converted into a single SFP plus form factor. So you don't need to have the bulky chassis that we saw in the earlier slides. It's going to be a single SFP that is going to take care of all the operations that your OLT used to do. Okay, and then on top of that, there will be a PON control that will be sitting on your access router, which will take care of all the controls or all the configuration or service provisioning that you have to do, and you can do it over a PON manager. Okay, so all the service provisioning without using the CLI and all that, you can directly go into a PON manager and then provision the services for your customer. Okay, so eliminating the need for a separate OLT chassis is the one benefit, and the functionality is on top of the SFP module, right? Okay. So how does it work? So as I told you, we will have a OLT that will be into a SFP plus form factor. We will having a PON controller on the router itself deployed as a container, and then a PON manager used for provisioning the services and managing the entire OLT chassis. And we can have multiple OLT chassis being managed by a single PON manager on the access router. Maybe your access router will have multiple ports. So all of those ports can be managed by a single access router or using these particular PON manager UI. What are the applications that, or what are the services that you can provision? You can automate your provisioning on the using these PON managers. Then you can have performance monitoring and diagnostics as well. Okay, all these things, all these features that are new coming up because you can now plug it directly on top of your access router itself. And then with the on the service configuration part, you can do any VLAN, specific VLAN that you put your customer into, maybe a service VLAN, then NNI networks, all these service provisioning, queue in queue, double tagging, everything you can do it in this particular PON manager for provisioning the service to your endpoints and to your ONTs. Right, and there's one more thing that also Mark also spoke about is about the digital subcarriers based NG-PON, where essentially you can have, so let's assume you are having a 200G link, okay, and you can have multiple subcarriers on top of that, which will essentially can be dynamically allocated, which means if suppose we are having optical splitter of 1:8 ratio, okay, and then we want to have only 3 or maybe 7, a total of 7 users that are essentially using these subcarriers. Now, one of the user want to have an additional bandwidth of, let's say, 50G. So we will having a 200G overall limit, and then we will having 8 subcarriers of 25G. So we can specify 2 specific subcarriers to a specific customer, using which it can have a higher bandwidth limits. What are the benefits out of it? You can have flexible bandwidth allocations, which you can perform for your customers. Secondly, if you're not using a specific subcarrier, then you can reduce the power requirements onto your device. And then future-ready designs. How you can do a future-ready design is basically if your customer plans to upgrade, or you or they want to have updated services or updated speeds onto your network, you can have it because of this. And because you are future ready, essentially you will be able to you don't need to perform truck rolls, that you don't need to send a guy to the field, he'll be changing all this infrastructure. Essentially you will just log into your subscriber management gateway, you will assign an additional subcarrier to that particular customer, and you're done with it. Okay, so we have talked about the PON technology as such. We have talked about the digital subcarrier based NG-PON and how the upstream and downstream transmission happen. Now for the completion of the whole session, we need to understand essentially how the endpoints or the subscribers are managed. Okay, to make sure that we are able to manage these subscriber, we need on top of this infrastructure something known as a BNG. So a BNG essentially makes sure that you are able to manage your subscriber that are sitting at your endpoint, your FTTX customer, maybe fiber to the home, curves, etc., enterprise, etc. Right. So to manage these customers, you need to have a BNG sitting on top of it. Okay. And what are the various components of BNG? So you need to first of all have a BNG router. then you'll be having a DHCP server, a Radius server. Okay, and this BNG router will have an end-to-end session with your endpoints or your ONTs. Now, what these sessions are going to be, essentially two protocols that we use of IP over Ethernet and PPPoE. So essentially, depending upon the use case, we would select which specific point-to-point protocol we want to use for this BNG session establishment. Okay. So let's take a look at how PPPoE session established onto a BNG router for the users in the case where we need a metered billing. So initially we would have a session between the ONT initialization and registration with the OLT that has to happen. Then the ONT part will send a request to the BNG for a DHCP discovery. Okay, once that happens, the BNG router offers a BNG reply to it, and then they form a specific PPP session, point-to-point protocol session. Once that happens, we need to have a AAA. Okay. Now, before we move to the AAA, we need to understand that these BNG routers can do the DHCP functionality into themselves as well. So we don't need to have a separate BNG. It depending upon the infrastructure, that's how you can do it. Okay. And now in the AAA part, we need to have authentication, authorization, and accounting. Essentially, if the specific end user has authorization to have the access or not, is he authenticated to do that or not? And first, and the most important thing, has he paid his bills or not? If he has paid his bill, he has some specific plan selected, then the session will move ahead. If he hasn't paid his bill, the session is essentially forward the user to some payment gateway page so that they can make their payments, and then based on that they can have their session completed. Okay, so if the payment is done, they will be moving ahead, and some bandwidth profile will be assigned to that particular user based on maybe which plan they have selected into their network. Based on that, they'll be selecting, and then finally an IP will be assigned. Similarly, for the IP over Ethernet, you will have the protocol flow as follows. Now, in this case, if you want to have the authentication part done, you can essentially use different options that we have, specifically option 82 from the DHCP server to have the authentication completed, and the rest all remains the same. Now, the previous one that we talked about, the PPPoE authentication, that is specific to when your session is based on metered billing. Maybe you want to have subscriber management and authentication specifically in the case of end users or broadband customers. And then when you want to have it based on if you want to have it deployed in a what we call it as an enterprise environment, then you can use the IP over Ethernet session or protocol. Okay, now what is new that is happening in the BNG case as well? Okay, so we have talked about we need to have a specific core router or a BNG router, which will form your IP over Ethernet session or PPPoE over Ethernet session, as we talked about. Now we can have all these functionality, that is the BNG functionality, in a virtualized environment. Okay, so with the vBNGs, you will need to have an NFV environment which will take care of or deploy these particular BNG onto your telco cloud. And even better, but the problem with this is that your control plane and your user plane is not separated in this case. Essentially, it puts additional overhead onto your virtualized router to process all the request or all the data that is coming from. So, and how can we solve this problem? Essentially with the CBNG or the control and user plane separation. Essentially with the CBNG, what you can do is you can have your control plane separated onto the telco cloud, and you can have your data plane or the user plane onto a separate router running as a container. Okay, so your control plane will take care of the policy management and subscriber IP provisioning, your IP pool, and your control plane or your user plane will take care of the policy enforcement. So whatever policies you have defined, it will enforce it using the user plane. Okay, so any specific subscriber termination has to be done. That will be done via this particular architecture. So physical BNG, virtualized BNG, and then a separation between the control plane and user plane. Right. So with this, let's now look at some of the new cases. There is a wide, broad thinking that
these specific BNGs or these specific PON technology that we talked of is only for broadband customers. But it's not the case. There are a lot of other use cases which we can perform. Maybe it could be in the common mall areas, premium lounges, corporate offices that are there, then basements and parking. So all these are running on IP network somehow. And then on top of that, we can use the PON controllers or the PON infrastructure. Right? We will have our ONT layer. On top of it, we will have the passive optical splitters and the OLT chases that we talked about in the previous slides. And then the core switch following the core routers and maybe the monitoring system, because all these places that we talked about or all these use cases we talked about will essentially have network management, storage units, and some monitoring centers. Okay, so even in these newer use cases, we can have even more optimized infrastructure. That is, as we talked about, the OLT chassis removal. So we can have the OLT chassis removed. We can have a core switch removed because all this functionality is now collapsed also from the user and also and from the routing point as well. So we can have and we don't need to have a core switch. We don't need to have bulky OLT chassis. We can have all the functionality of the OLT chassis integrated into this SFP, which will essentially reduce the complexity of your overall network. And then eventually you get cost savings out of it. So new use cases with the newer infrastructure with the cost savings. With this, let's move to the key takeaways of for the session today, and let's go through a brief on what we talked about and how these specific technologies are advancing us towards. So first of all, we talked about the cost-effective broadband technology, essentially the PON technology, and how it has evolved to get us to the network where we are. Okay, and then we need to understand that these technologies are evolving. Initially, we had very lower speeds. We are now going up to 10G symmetrical PON and beyond over in these speeds. Okay, the next thing that we need to understand is that the routed PON architecture, that is splitting or essentially removing your OLT and taking it as a SFP. These kind of optimizations are much needed in your infrastructure to make sure that you have an optimized infrastructure overall. Okay, because you can have a better traffic management, you can have management scalability, cost savings, and everything. And next will be the newer technology in the PON that we talked about, the digital subcarrier based NG-PON, where you have dynamic nature of the subscriber management that you can perform. And also in the BNG side, where you can have the control plane and user plane separations. With this, I would like to close the session on a note that there are enormous possibilities that are waiting to be unlocked with this extended capacity and features with these technologies. Thank you. Any questions?
Hello. Yep. Thank you. Are there any questions? Appreciating that the coffee is awaiting, but all right. Well, I will have a question. So you mentioned sort of speeds of up to 50 gigabits per second. So what's the sort of practical upper limit for this type of technology in these types of use cases?
So we are having so the broadband customers, the user requirements are increasing, right? So at some point of time, the current infrastructure is going to get absolute, and we need to have higher speeds. And over there, we would need the symmetrical bandwidth, because essentially we are now generating traffic from both ends, right? Initially, we used to have, you can say, full HD or HD kind of uploads that you used to do, but now you have moved up to 8K or 16K kind of uploads. So based on that, for the future, you do need such kind of infrastructure, and you have to make sure that it is ready for the future.
All right. Thank you very much. Okay. Any questions? Okay. I'd like to thank you again.
Thank you.
All right, that brings us to the end of this session. Thank you to the three speakers. Coffee outside. So next session, I think, is starting at, I guess it's 11:30. But we'll see you back there then. So again, thanks very much. And it was a good session.